All right, happy new year. We are moving on to chapter 6 here, the skeletal system. And this is really just the chapter about, bones as tissues and kind of bones in general, how they're formed and, kind of the structural functional cells within bones and stuff. So this is really the first chapter before we really get into some of the meat of what's going to be a lot of pretty heavy memorization, because right after this is the axial skeleton, which is only 28 bones. But then we're going to quickly move into the, I'm sorry, it's not 28 bones, it's 28 pages. It's 80 bones. And then chapter 8, we're going to get into the appendicular skeleton, which is 126 bones. So skeletal system in total is going to comprise of 206 bones. So chapter 7 and 8, just a lot of just kind of raw memorization here. But before that, let's get through chapter 6. All right, so we're talking about the skeletal system and its major functions. So when our muscles contract, they're going to pull against those bones. They're going to do everything. They're going to make us sit, stand, run. And even at rest, even me sitting down right now, my muscles are helping, keep me erect in this chair. When you're standing, obviously, a lot of muscles are helping you out, even while you're lying down. So when you think that you're at rest, your muscles are still, always kind of constantly at work. Obviously, when you're running or lifting weights or doing something more physical, other muscles are going to kind of kick into overdrive. All right, so functions here. Skeletal system does include cartilages, ligaments, and other connective tissue that are going to stabilize and interconnect those bones. Our bones provide us with support. They actually store minerals and lipids, an example being calcium salts. They're going to produce blood cells, so erythrocytes, red blood cells, leukocytes, white blood cells, and others are produced in the marrow, in the red bone marrow, which fills those internal cavities of many bones. They're going to offer protection, like our rib cage, for example, and leverage as well. Our bones are going to kind of act as levers for us to be able to perform work, all right? And bones themselves in the anatomy lab are very different than when they are alive in the body. We'll kind of learn a little bit more about that as we go on. So they're classified according to shape and structure, and they have a variety of markings. So you may have heard of some of these before. So we have sutural bones like those in the skull or the cranium. They're flat, and oddly shaped. They can range in size. Their borders are like pieces of a jigsaw puzzle. So you can see that here in the posterior view of the cranium here. So they're sutural bones, but they're also flat bones as well. All right. Yeah. Okay. Irregular bones are like those of our spinal column, our vertebra. We have short bones. There's really small, kind of like cube-shaped bones in our feet and our hands. Those are called short bones. Sesamoid bones are kind of a little bit more irregular. The patella, the kneecap is going to be an example of that. And long bones are kind of like the more traditional bones we're used to. The humerus, the radius, the ulna, femur, tibia, fibula, things like that. All right. So then we have some bone markings. So openings of bones are going to be called foramens. Usually they're rounded passageways, and blood vessels and nerves are going to pass through those. All right. Chambers kind of within bones themselves, and you can see that here in the skull. This is one of our sinuses. So it's a chamber within the bone, normally filled with air. We have fissures, which are deep furrow, a cleft, or a slit. We can see this here in the posterior of the occipital kind of socket here. A meatus, which is like a passage or channel, especially the opening of a canal. So kind of similar to a foramen. Canal is a duct or channel. We have a process, which you'll hear a lot, which is just like a bump or a projection. All right. We have things called trochanters, which are large, rough projections. So you can see one here on the femur here. This will be on the lateral side. A head, this is our hip socket here of the femur. The neck is going to connect that head to the main body here. A facet is like a little flat surface. A condyle is kind of like when you see like cartoon dog bones, and it's just like, you know, there's two heads and there's kind of an internal part. That's kind of like the condyle. That's that smooth process like in between, pretty sure. We also have something called a trochlea. I mean, there's a lot here. A sulcus is a narrow groove. A fossa, which you'll hear a lot about, that's a shallow depression. A lot of times, like glands, like our pituitary, will be placed within fossas. All right, a spine, not our spine, but a spine of a bone, like off of the pelvic girdle here. A crest is a prominent ridge, just a line. So yeah, so it's just some of the kind of vocab here that we'll be using as we talk about the bones. All right, so a little bit more about bone structures. This is like just a generic bone. I mean, pretty much the femur here. So we have the diaphysis. Make sure I'm saying that right. It's probably diaphysis.
Diaphysis.
Yeah, diaphysis. That's the extended tubular shaft. All right. At each end is an expanded area called the epiphysis.
Epiphysis.
Epiphysis. And between this little part here is called the metaphysis, which is going to be kind of what connects the two. So it's a palindrome, EMD-ME. All right. So the diaphysis in the middle, epiphysis on the ends, and then the metaphysis in the, I have to stop saying these words, in between. All right, so bone itself is composed of matrix and several types of cells: osteogenic cells, osteoblasts, osteocytes, and osteoclasts. So we will remember, we will dive into those. So remember, so bone tissue itself is supporting connective tissue. The matrix, that inside part, it's very dense due to deposits of calcium salts around protein fibers. The matrix has osteocytes within these pockets called lacunae. Canaliculi are narrow passageways through the matrix that extend between the lacunae and nearby blood vessels, which is how osteocytes, bone cells, get nutrients and exchange waste. And then we have something called the periosteum, which covers bone except at joints. All right, so let's look about the bone matrix. So this is where we have calcium phosphate, and this makes up almost 2/3 of the weight of bone. It interacts with calcium hydroxide, CaOH2, to form crystals called hydroxyapatite. The other third of the bone are made of collagen fibers. All right, so we have calcium phosphate making up 2/3. That's Ca3PO42. So you have that phosphate and you have that calcium. And then you have 1/3 of collagen fibers, which we should remember are those strong fibers that we learned about in the tissue chapter. So calcium phosphate crystals are very hard, but relatively inflexible and brittle. So think about how relatively easy it can be to break a bone. They can withstand compression. So like if this is the bone, it can stand compression if there's weight coming from here or here, but are relatively inflexible. But shatter with twisting, bending, or sudden impact. Okay, so collagen fibers, as we know, are remarkably strong. As we learned before, when pulled, they are stronger than steel. They can also tolerate twisting and bending. So if you have even like a chicken bone, try to twist it or try to pull it, nothing's really going to happen. But snap it in half, even like a wishbone, that thing's going to break pretty easily. All right. So without that calcified matrix, bones are bendy like a piece of grass. These crystals plus fibers are a protein crystal combination with the flexibility of that steel-like collagen and the compressive strength of hydroxyapatite crystals. So bone is superior to concrete. That's pretty cool. All right, so we're going to enter mesenchymal, which is, they mean stem cells, so mesenchymal stem cells. And bone stem cells are called osteogenic cells. So osteo meaning bone, genic meaning, birth or creation. And these are going to produce daughter cells that become osteoblasts. So you can easily remember what an osteoblast does because of the B, and you can think of that as a builder. So osteoblasts are going to produce, they're going to build bone. They're going to produce new bone matrix. All right. Just like fibroblasts that we learned about with connective tissue are fiber builders. All right. Creation of new bone matrix is called osteogenesis or ossification. And the matrix they create is called osteoid and is an organic matrix. All right. So straight up, osteocytes are mature bone cells. So you have the mesenchymal stem cells called osteogenic cells. They're going to produce daughter cells that become those osteoblasts. Osteocytes is just a term for a mature bone cell. Okay. They occupy a lacuna. You have one osteocyte per one lacuna, and we'll take a picture. We'll take a look at a picture of this in a second. All right. Bone cells cannot divide. So we'll figure out how that works in a second. So osteocytes, again, this mature bone cells, are going to maintain the protein and mineral content of bone matrix. They're also going to take part in the repair of damaged bone. If released from the lacuna, it can convert to another type of cell like an osteoblast to aid in repair. So we are producing bone cell. They're just not undergoing mitosis. They're not dividing. All right. Osteoclasts. We have osteoblasts, which build. Osteoclasts are little recyclers. They're kind of like the bone maintenance men or women. They're important in the regulation of calcium and phosphate ion concentration. So the Ca3PO42, when that dissociates, you have calcium ions. They would be cations. No, they would be cations. They'd be positive. And the phosphate, PO4, which I guess would be 2- would be that anion. All right. So they're going to regulate all these ions that are going on, especially in relation to body fluids. They're also going to erode bone matrix. That's called osteolysis. So lysis meaning cell death or cell bursting, osteo meaning bone. Okay. So compact bone contains parallel, something called osteons. The spongy bone contains trabeculae. So compact bone protects, supports, and resists stress. And then we have spongy bone that provides some support, but also stores marrow. It's me, marrow. All right. Compact bone is all about the osteon. It's the basic functional unit of mature contact bone. All right. So we were talking about like lacunae, weren't we? Here we have those osteons. Here we go. We were talking about those osteocytes, those maintenance people that are in a lacuna here, the canaliculi. Here's the osteoclasts. I'm sorry, osteocyte is a mature bone cell. Osteoclasts are those maintenance cells. All right. So that's that there. So yeah, a lot of stuff going on. Osteogenic cells here in this kind of basement membrane. Those are going to create daughter cells. Osteoblasts, these are the builders here. So it looks like the osteogenic cell here becomes an osteoblast. But let's go through this. All right. The osteon is the circular cake thing. So that is this is an osteon. You can see these circles here. These are osteons. So we're kind of lifting this up and we're looking at this. This whole thing is an osteon. In the very center is a central canal with blood vessels. We have blood vessels in our bones. I never knew that. You also have those perforating stuff, like you cracked a bone open, there'd be like blood vessels hanging out. That's pretty gross. You also have these perforating canals. So I think that's the same thing. Then we have something called lamellae. Let's see if we can find this on the picture, or lamella. These little like tiger lines here, which are simply layers of bone. So lamellae, layers of bone. There are three kinds there are three kinds: concentric, which are part of osteons; circumferential, which surround the entire thing. This is circumferential lamellae here. And interstitial, which you can see these little triangles here, okay? It's beautiful, really. I mean, it kind of is. A single osteon is like a drinking straw with very thick walls, and you can see that here. When you try to push or pull the ends of a straw together, it's very hard, but from the side, it bends like a limp noodle. For this reason, the femur can withstand 10 to 15 times the body's weight, yet a much smaller force from the side can break it. All right, so it makes sense. So look at the way, here are main arteries and veins, and they straight up, there's holes on the surface of the bone here, and they connect to this blood network. All right. So when we have spongy bone, where our lamellae or layers of bone are not organized into osteons, so that is this, they are instead formed into a meshwork of fibers called trabeculae. So that's what this is. They are oriented along stress lines and extensively cross-braced and are extensively cross-braced. Spongy bone itself is found where bones are not heavily stressed, or where stress can originate in many directions. It is also naturally less dense than compact bone, so it reduces the weight of the skeleton, making it easier for muscles to move bones. So you can see here, this is where that trabeculae would be. This kind of yellow portion here is where we would have all of this osteon action here. All right. Spongy bone itself has no blood supply, so we could see there's no blood vessels running through here. They contain, this is where the red bone marrow is, which forms red blood cells. Can also contain yellow bone marrow, but that is just adipose tissue, and it's used as an energy reserve. So that's pretty cool. So here we have that periosteum here, which covers the outside of the bone as a fibrous and an intercellular layer. Collagen fibers of the periosteum are continuous with those of the bone. So you could see a fiber here connecting through adjacent joint capsules and attached tendons and ligaments. We have those canaliculi, which are narrow passageways. So there you have the bone matrix. The endosteum is an incomplete cellular layer containing osteoblasts, osteogenic cells, and osteoclasts. All right, so how do bones form? There are two ways that ossification or bone formation occurs. We have endochondral ossification. That's where bone actually replaces existing cartilage in length via interstitial growth, and in width by appositional growth. This is like that maxi-pad image that was in the book, whatever. Intramembranous ossification is where bone develops directly from mesenchyme, again, stem cells, mesenchymal, or fibrous connective tissue. So not too much detail there. All right, 6.6, bone growth and development depend on bone remodeling. So bone remodeling is a thing. It constantly recycles and renews the organic and mineral components of the bone. It involves that interplay of those osteocyte, those like daughter cells, right? No, not the daughter cells. Those are just the generic mature bone cells. Osteoblasts, the builders, osteoclasts, the maintainers. Osteocytes are continuously removing and replacing calcium salts. Osteoclasts are constantly removing bone matrix, and osteoblasts are always adding to it. All right. So people who subject their bones to muscular stress actually get stronger muscle and stronger bones. That's pretty crazy. Exercise, nutrition, and hormones affect our bone development and the skeletal system. All right. So after a few weeks, unstressed bones can lose up to 1/3 of their mass. So if you're not up and at 'em and moving, 1/3 of the mass, that's crazy. We do need a constant dietary source of calcium and phosphorus, those two ions, for bone growth and maintenance. Magnesium, fluoride, iron, and manganese are also important. Calcitriol and vitamin D3 are essential for calcium and phosphate absorption. Vitamin C, a deficiency of vitamin C, which is called scurvy, is a loss of bone mass and strength. And sex hormones at puberty, rising levels of estrogen, testosterone stimulate osteoblasts to produce bone faster. Estrogen causes faster epiphyseal closure, making women shorter than men. That's crazy. Epiphyseal closure. So this part here, that's fascinating. To do with estrogen. All right. Calcium plays a critical, I guess that, I guess it closes earlier and the male bones keep growing more, which make us taller. I guess that makes sense. All right. Calcium is the most abundant mineral in the human body. We contain 2.2 to 4.4 pounds of this stuff. 99% of it is in our bones. As we know, calcium ions are important for plasma membranes. We do. Oh yes, obviously they're going through our cell membranes and the intracellular activities of neurons and muscle cells, especially cardiac cells. If our calcium increases by 30%, our neurons and muscle cells become unresponsive. If it decreases by 35%, we go into convulsions. Holy shit. 50% straight up gone, death. 50% reduction in calcium, gone. It's very closely regulated. So what regulates this? Two opposing hormones. These are in the thyroid. Our parathyroid hormone increases calcium level, and our calcitonin, I like to think of, tones in that calcium. It lessens calcium absorption. So if I go into my hormone guide, and we go down to the thyroid, we have both of them here. So calcitonin is in the clear cells of our thyroid. They target our kidneys and bone. They get rid of calcium by excretion in the kidneys with fluid and prevent calcium absorption in the digestive tract. So it's like we have way too much. We're going to get them out of here. All right. The parathyroid hormone, here's the thyroid hormone here. Parathyroid, which are these little purple guys on the back of the thyroid, which is in our neck. They're going to increase calcium via osteoblasts as builders and osteoclasts as recyclers. Kidneys are going to reabsorb calcium via what's called calcitriol. If we go down to our kidneys, a hormone called calcitriol, which is triggered by that parathyroid hormone, stimulates calcium and phosphate ion absorption in the digestive tract, works with that PTH, which holds on to calcium. Cholecalciferol, which is vitamin D3. Yes, the sun one. Were we just talking about that? Yes, we were. Okay, here we go. Calcitriol and vitamin D3 is converted to calcitriol. This is mentioned a lot in the bone chapter. So there you go. Little preview of our endocrine chapter, which is my favorite one. All right, let's talk about bone fractures. So we have an open or a compound fracture. Those are the same thing. That's when the bone is sticking through the skin, or a closed or simple fracture. So yeah, so open fractures protrude through the skin. open compound. So this picture here is kind of the repair of a fracture. So we have the break here. We have these bone fragments. So we have something called a fracture hematoma. Immediately after the fracture, extensive bleeding occurs. A large blood clot or fracture hematoma soon closes off the injured vessels and leaves a fibrous meshwork in the damaged areas. It's like some quick damage control. This disruption of circulation kills local osteocytes, or recyclers, broadening the area affected. Dead bone soon extends along the shaft in either direction. So this, the external bone here is starting to repair itself, the periosteum, and then the internal bone. So it's called a callus. The cells of the intact endosteum and periosteum, so inside, outside, undergo rapid cycles of cell division. I thought they couldn't divide, and the daughter cells migrate into the fracture zone, this whole fracture hematoma. An internal callus forms as a network of spongy bone unites the inner edges of the fracture. An external callus of cartilage and bone, I guess, encircles and stabilizes the outer edges of the fracture. So here is kind of this end part. There's an internal callus, there's an external callus. Osteoblasts are going to do their job and build. Fragments of that dead bone are resorbed and replaced. And the ends of the fracture are now held firmly and can withstand normal stresses from contractions. So a swelling, look at this external callus. A swelling initially marks the location of the fracture. Over time, this region will be remodeled by osteoblasts and osteoclasts, and little evidence of the fracture will remain. The repair may be good as new, or get this, the bone may be slightly thicker and stronger than normal at the fracture site. Under comparable stresses, if you have the same injury, a second fracture will probably happen at a different site because this is now a strong point. Last little section here, osteopenia. So inadequate ossification or bone building is known as osteopenia. This can, this reduction of bone mass begins between 30 and 40. Hey, I'm 32, I'm losing bone mass, wonderful. The bone builders, osteoblasts, slow down that they're building, but the osteoclasts keep recycling. Well, that's good. But basically what's happening is, oh, it's not good actually, because we're not building, but we're throwing away. So our bones are basically eating themselves from the inside. That's horrifying. The matrix is being eroded. Osteopenia itself causes what we hear, osteoporosis. So pores or holes in the bone. And that's going to compromise function. It makes our bones fragile and brittle. Over the age of 45, a third of women and 18% of men have osteoporosis. That's it. It's the end of the bone chapter. We will see you in chapter 7, which is pretty fun because we're going to talk about the axial skeleton.